Hello everyone and welcome into yet another live stream, and today we will be researching things and stuff. Yes, hi damn it, hi the who, hi, welcome everyone, hi. Hi Dark Vader. Yeah, I guess I will just... Hi the Joshua. Should I take the pill before this live stream? No, yeah, you are right, I should. Makes for longer and more fun live streams. Okay, so, hi there everyone. And for this very special day, day 440, it's special because it has a 0 at the end, we will be doing more of the same. Again. Yay. Hold on. There we go. Yay! Remember the question you asked yesterday about meth? Which one? Wait, I asked about meth yesterday? I don't remember that. Oh, if it's illegal to like... Yeah, that wasn't about meth. That was about... I got an answer. Yes, you can if you change the title and don't mention anything about meth. Oh, no, I did... not meth, amphetamines. There's a difference. Amphetamines are... had more legal. Don't mention anything about me. You think it might improve YouTube. I find it hard to believe. I would need to see a video. I would need to see the video to actually... No, I really find it hard to believe. Hi, Toby. Hi. Anyhow, oh yeah, one thing, which is pretty fun. If you remember, the main reason why we started researching this textbook is chapter number 3, which is right here. If we go in chapter number 3, which is the oh, why is it loading for a long time? Electrical properties, precisely. That's the chapter we actually wanted to get to, because it has all the fun bits like... Why is it loading for sure? It's like text. It has bonding in semiconductors, semiconductors, p-n junction, diode, MOSFETs, all of these fun things which we actually want to get into. And what's really fun is that we are actually only 6 chapters away. Right now we're in the chapter number 6, then we only have chapter 7, 8, 2.1, 2.2, 2.3, 2.4, 2.5, 2.6, that's actually 7, never mind. And then we'll finally get into electrical properties, which is what we actually wanted from this textbook in the first place. Oh my goodness, hi the Tefta, it really took us a while and it will take us a while, and then we can get into other fun stuff like organic chemistry or something. Anyway, the point is, models of chemical bonding. Wait, did we get through? I feel like we got through them, right? We got through the, oh yeah, we got up to the quantum ones, right? Oh, of course. There's always quantum ones. Actually, Toby, I can ignore you. And you know what? Just to prove how I can ignore you, I'm gonna ignore you from now on. Because you can't tell me what I can and can't do, alright? Don't tell me what I can and can't do. The only one who can judge me is... I don't really have a good punchline for that. And the setup was there, but I couldn't find the thing. Hold on. I got milk. Okay. Also, no, Tefta, I got a question. Tefta, I actually have a question for you. You know what? I'm glad you joined in, because I actually have a question. You see, I ordered some MOSFETs online. 6 of them, to be exact. And my question may be a bit odd. It's gonna be a bit of an odd question, but like... in the package, there was a piece of candy. Is that normal? I guess my question is... I actually have it right here. Can you turn on the music a little bit? Of course. Yeah, sorry, I always start these streams. There we go. And my main question being obviously that, you know, is it safe because a random, you know, when you find a random piece of candy in a package you ordered from Lord knows where. I have a request. Could you rush through your notes so I could revise? I'm too tired now to recall anything. Oh, don't worry. There isn't really much to revise on. I have no idea what I'm doing. But you know what? That's a good idea. We should do it. Only received candy from Ultimate Robotics when I ordered and sent it. I wouldn't take candy from a stranger. I love the idea of just getting candy with all of the electronics stuff. In fact, I love that idea. Either I think it's laced. I'm decently certain. So you know. For the sake of the live stream, let's say for now not. Okay, let's go through everything we've learned so far. Let's revise. We have 3 pages of notes, which is not a lot, but let's go through it anyway. Okay. So we have intensive properties, extensive properties. So intensive properties is just general properties, like for example, general properties of some sort of substance, and extensive is properties of a certain amount of substance. So for example, when it comes to iron, you have the conductivity of iron. That's an intensive property. And then extensive property, which is basically how many kilograms of iron you have, right? So that's the difference. Why rod? What's rod doing there? Hold on, what is rod doing there? Intensive properties have 2 characterized matter. Why does my notes are a mess. My notes are a pure mess. Then we have some boring stuff. Work, transfer of energy. We have some boring stuff. This is still some boring stuff because all pretty simple. Then we have quantum mechanics. Then we have oh, this is cool. This is the gas laws, right? So this, which basically tells us how gases behave. You can read through the rules if you want right now. There's a kinematic gas theory, I think it's called. I don't remember. It's basically gas theory. And then we have root mean square velocity. So basically an average, a certain kind of average of velocity in gases. And then it's also equal to T, where T is the absolute temperature and M is the molar mass. So the kind of average, I'm saying kind of average because this is an average, but not the average, you know, we usually think of. So the kind of average, velocity of a single particle in gas would be equal to the absolute temperature divided by molar mass square root. Then we have this, which is about the energy states. Honestly, all of this is just seems kind of irrelevant. now I'm thinking about this, I feel like we might be going over way too many things. Oh, this is cool. This is actually us just deriving the epsilon value. And then we have different bonding types. And that's where we are right now. Honestly, all of this really seems irrelevant to what we are actually supposed to get to. But you never know, maybe we'll come down to later on. The point is quantum mechanical models. So yeah, so this is basically you know, bonding models except for quantum. And what are we actually supposed to get to? I am so glad you asked. We're actually supposed to get to the 3rd chapter, electrical properties. I want to understand how transistors work because I don't get it. I have no idea how they work. This, or actually this. If we get to the 3rd chapter, 3rd and half, 3rd.5, 3rd chapter, 5th subchapter, then I'll be satisfied. Because I have no idea how transistors work. Absolutely no idea. And that's why, you know, we want to get through the textbook. And then we'll use the bonds. Well, we already know how bonds work, right? Okay, hybrid orbital model. We don't care about history. It's based on the premise that that if the atomic s, p, and d orbitals occupied by valence electrons of the adjacent atoms are combined in a suitable way, the hybrid orbitals that result will have the character and direction properties that are consistent with the bonding pattern in the molecule. The rules for bringing about these combinations turn out to be remarkably simple, so ones will count. Wait, we've been over this too. 3.5. I know. My man's learning because he could have watched a 30-minute video on YouTube about it. Try it if you want. You know what, Damek? Try it and see how it goes. Go. No. Try it. Go and watch a tutorial about transistors, how they work. Come back and try to explain how they work based on that video. Go right ahead. Trust me, it's not as easy as it sounds. From tutorials, you can learn how to use transistors. But it gives you absolutely no information about exactly... It's witchcraft. This is the first source I found, which is actually going into the underlying chemistry of the P and N semiconductor things. So we tell you about... this isn't really any bond theory to understand MOSFETs and transistors. Yeah, but like... I know I don't need bond theory, but... Two things. First of all, I already know bond theory, actually. I already know these models. I know if I mentioned... I feel like I mentioned that a couple of streams, on a couple of different live streams, but I already know these because I already researched it for another video. But another thing is that whilst I don't need bond theory and other things, I don't really know what I need to know. And so that's why we're going, chapter by chapter. Learning about bonds for transistors is dope though. It really is. I really like... Because, once we actually get to MOSFETs, we will understand them perfectly. And I mean perfectly. We'll understand everything. Everything will be clear because we'll know all of the underlying chemistry. For goodness sake, we're about to... The goal of these live streams is to understand how an electrical component works based on the underlying chemistry. That's cool. That is in my opinion. You need to know that atoms stick together in a solid, and then the book will probably go into semiconductor physics. Oh wait, we've been over all of these. Oh yeah, these are just summaries. I remember now. I don't know. I mean, all I remember is that the first live stream, when I actually wanted to understand how transistors work, I went straight for the transistors chapter and got really confused. So, and also, oh yeah, and also another thing. After this, our next topic of research, because once I'm done with this book, I'm not gonna just stop researching stuff. Once we're done with this book, our next topic of research will be organic chemistry, and this kind of feels useful, right? When it comes to organic chemistry, it feels kind of useful. I think. Yeah, at least in my opinion, I think so. Because this is like material science, so this is basically, these first chapters are the basis for all of chemistry. Organic chemistry, yeah, indeed. Everyone's favorite, everyone loves the organic chemistry, right? Organic chemistry, it's fun, everyone loves organic chemistry. Speaking of it, precisely. I like me some CH3, CH. No, that's actually the easiest bit, in my personal opinion. The large molecules, that's the easy bit of organic chemistry. The difficult bit of organic chemistry is the fact that it's really precise. So you have large molecules which are dependent on orbitals, for example. And no, that's leads to all sorts of problems. Okay, let's go. Electronegativity. Electronegativity of an atom denotes its relative electron attracting power in a chemical bond. It is important. Okay, so let's first note this down. Solid definition. In my personal opinion, electronegativity is the relative electron attracting power. So basically, when we have the polar covalent bond, the atom with the higher electronegativity will get the, in quotations, bigger share of the electron. That's it. I am like Shakespeare when it comes to words, honestly. It is important to understand that electronegativity is not a measurable property of an atom in the sense that ionization energies and electron affinities are, although it can be correlated with both of these properties. Cool, so it's a social construct. The actual electron attracting power of an atom depends in part on its chemical environment, that is, on what other atoms are bonded to it. So tabulated electronegativities should be regarded as no more than predictors of the behavior of electrons. Especially in more complicated molecules, there are several ways of computing electronegativities, which are expressed on an arbitrary scale. It doesn't feel like science. I mean, I know it's science, but it feels like the kind of science I really don't like. The concept of electronegativity was introduced by Linus Pauling, and his 0 to 4 scale continues to be the most widely used. So I don't like this. The 0 to 4 electronegativity scale of Pauling is the best known of several arbitrary scales of this kind. So negativity values are not directly observable but are derived from measurable atomic properties. Okay, they are derived from actual measurable atomic properties. So you can call it negative 4 scale. No, it would have to be a 4 electro scale, because you know the negativity with minus cancels out. So ionization energy, electron affinity. The place of any atom on this scale provides a good indication of its ability to compete with another atom in attracting shared electron pair to it, but the presence of bonds to other atoms and less reliable. Okay, so the more complex something is, the less accurate electronegative scale becomes. Cool, that's neat. An atom that has a small electronegativity is said to be electropositive. But it has a small one, not a positive. It's clear that chemists hate mathematics, honestly. As the diagram shows, the metallic elements are generally electropositive. The electron of high... Okay, so... electropositive atoms... Wait, atoms, particles, molecules, atoms. Atoms. Positive atoms have low electronegativity. They are called electropositive because chemists hate mathematics. Alright. But on average, it will have a smaller share of the electron become the positive end of the bond, you see. Okay, but like... Okay, I don't wanna get off on a, you know, make it more tangent, but chemists are bloody awful when it comes to positives and negatives. Okay? I don't want to start another... make it more situation here, but like, chemists are pretty bloody awful when it comes to positives and negatives. You have an electron, which has a... Can't even say, was it an ion? Okay, you have an electron, which has a negative charge. And when you have an additional electron, that's why you note it down as negative, which means that negative means having more electrons. When you note down, you know, a particle as in H minus, for example, that is a hydrogen with one additional electron, because minus means adding an electron. That's obvious, right? Then you have electronegativity, which is used to describe the relative electron attracting power. Now, why is that? Well, it's because, you see, electrons have a negative... electrons have a negative charge, so when something is electronegative, of course, that means it attracts negative things stronger, right? Because when something is negative, it attracts other negative things. That's how it works, right? That's why it's called electronegativity. So the greater electronegativity, the stronger it attracts the electrons. If something is electropositive, though, then it's not attracting electrons, right? So when electropositive thing comes in contact with a negative electron, then it's not attracting as strongly because opposites obviously don't attract, right? So like it's simple stuff. I don't know why anyone would be confused by that. It's simple stuff in my opinion. Negative and positive, and also like electricity generally like flows from minus to plus, but it actually flows from plus to minus, but actually it flows from minus to plus, you know. Positives attract negatives? No, not in this case. Electropositive things actually don't attract. I can't wait for the chapter that introduces electron volts. Oh my goodness, no. It's gonna confuse you. Come on. Dipole moment. You know what? This live stream is just one massive dipole moment. When non-identical atoms are joined in covalent bonds, the electron pair will be attracted more strongly to the atom that has higher electronegativity. Because electronegative atoms attract negative electrons because because when you have something that's negative and something that's negative, and they both attract. That's simple naming convention. As a consequence, the electrons will not be shared equally. The center of negative charges in the molecule will be displaced from the center of positive charge. What did I just read? The center of negative charges in the molecule will be displaced from the center of positive charge. Okay. Such bonds are said to be polar, that's what I mentioned earlier on, and to possess partial ionic character, and they may confer a polar nature on the molecule as a whole. The center of the negative charges in the molecule will be displaced from the center of positive charge, which means that the center of positive charge will be in a different spot the center of negative charge. That's not the part I'm getting. I was confused with. Okay, I think I get it. So the center of negative charges is in a different spot than the center of positive charges. Also, are the rules in Make It Discord actually enforced? Asking so I don't have to worry. I don't know. Ask Elliot. Elliot is the... it's... Wait. Never been more serious. Yeah, so, yeah, they are actually enforced. If you break them, you're getting banned. Immediately. Actually. Yeah. There are no warnings. It's a PEM ban. It's also an IP ban too, so that if anyone ever joins in on an account with the same IP address as your previous one, they're also getting banned. Oh, from the same machine. If you have the same MAC address with a different account, then that account is also getting banned. Or if that account was created on the machine with the same MAC address, then. Or if it was created in the same room as the other account, then it's also getting banned. Or if it was created in at the same time, like, you know, the same day, then it's also getting banned. Anyhow, dipole moments. Polar molecule acts as an electric dipole, which can interact with the polar molecule acts as an electric dipole, which can interact with electric fields that are created artificially or that arise from nearby ions or polar molecules. Dipoles are conventionally represented as arrows pointing in the direction of the negative end. Okay. Arrows point in the negative direction. Negative what? Negative end. So they point at the negative center? From plus to minus. So from positive center negative. End. Why end? Doesn't... You know what? I'm overthinking it. The magnitude of that interaction with the electric field is given by the permanent electric dipole moment of the molecule. The dipole moment corresponding to an individual bond or to a diatomic molecule is given by the product of the quantity of charge displaced Q and the bond length R. This actually, you know what? This actually seems like we're getting into the useful bits. So, given by the product of the quantity of charge displaced and the bond length R. This makes sense. We have quantity of charge, bond length, we multiply them, and we get the dipole moment of a bond. Wait, why do we multiply the length of the bond by the amount of charge displaced? I feel like it's more of a definition for dipole moment then. Okay, in SI units, Q is expressed in coulombs, inverse amperes, right? I think. Or amperes multiplied by 10. It doesn't matter. The point is, and R in meters. So mu micro whatever. That has I don't care at this point. Has dimensions of coulombs per meter. If one entire electron charge is displaced by 100 picometers, a typical bond length, then the dipole moment is equal to 48 d. Is that the okay? Let's note this down. Let's note it down. Okay, yeah. I get it. Is this mu? Oh, I'm good. Oh, I'm so intelligent and smart. I mean, I don't get this, but at least I know the Greek alphabet, so you know. I count this as a win. Okay, mu is equal to Q times R, where Q is the charge displaced in coulombs. These spell coulombs. Coulombs. R is the bond length in meters, and this is the dipole moment in D. Mu and R are vector here. Yes, makes... Wait, R is the vector? Why is R a vector? Length... Wait, why is R a vector? Couldn't you do it with R not being a vector? Oh, so dipole moment is not a scalar. Oh, I see. Separation vector of two charge centers. Wait, never mind. I don't see. I'm blind. Why don't add you friends in the live streams? Wait, do you mean why don't add your friends in the live streams, or why don't add you friends in live streams? Because one seems like a suggestion and the other one seems like a threat, honestly. Wait, how is the separation vector of two charge? I'm gonna confuse you. You already did. Hold on. How is the separation vector of two charges? Well, I said I see, but apparently I don't. I think I'm hallucinating more than seeing at this point. Okay, it kind of makes sense. Wait, no, it doesn't. It doesn't. Well, I'm lying to myself. I'm in denial. That's what is happening. So, separation vector of the two charge centers. So, it's the... Coulomb's law, festive. Precisely what I'm looking for. Physics info. There's a website, physics info. Internet is an amazing place. Coulomb's law, yeah. Magnitude charge of two objects. Separation between charges. This, yes. What I'm looking for exactly. I'm looking for R because how it's defined. Yeah, I think I get it, but no, I don't trust myself. Can I get the definition of separation between charges? I'd rather get the definition than pretend like I define myself. Coulomb's law, yes. Give me... I'm... I'm sorry, Alex, I can't. Sorry, Alex, I don't have permission. Yeah. I'm not allowed. Represents the distance of separation between the two objects. So, so is it the distance between the positive center and negative center? I should just ask that instead of trying to look it up. Is that what R is? Is that what this is? The difference between the positive center and negative center. But wait, would that be then difference between positive center and negative center, or difference between negative center and positive center? Which way? Because it can't be the magnitude, because it's... Unless it can't be the magnitude, it can be vector of magnitudes. It is starting at the positive center and points to the negative center. So what is the difference between them? Unless it's not. Is it? I have no idea what I'm doing. Hold on, let me check up on the animation in the background in the meantime. Ooh, one is almost done. I'm just gonna try something in the background in the meantime while we're, while I'm struggling. Starting positive center and points to negative center. Hold on. Starting a positive. So it's negative minus the positive. Is it? Then they would make sense as a vector. Hold on, I'm animating the background because the animation finished rendering, so I feel like it might as well. Chemistry of crack cocaine when... That's biochemistry at that point. That's a really difficult one. Found this link, hope it helps. I should have to do this. Okay, so electric dipole D. Yes. Okay. But distance D. Is D R in this case? Is D just R? What a phenomenal question to ask. Is D just R? It is, right? Just agree. It doesn't matter if I'm right or wrong. Yeah. Oh, it is. Okay, cool. Yes. Okay, then I get it. Okay, then it's all clear. Okay. All right, then clear as spring water, simple enough. And now it makes sense as a vector. This being a vector, and obviously if you multiply a vector by a scalar, then you're gonna end up with a vector. And so the dipole moment would be this multiplied by this. So basically the charge... so this would be then the charge display. It makes sense. Okay, it all makes sense. Kind of, so much. I don't want to get too much into it because it then won't make sense anymore. So we're multiplying the vector of how... oh, it makes so much sense now. So you have like... Hold on, let me bring out paint. Oh, hold on. Oh, let's see if I'm getting it. If I'm getting it, then that's good. That's good news. If I'm not getting it, then just nod and pretend I'm getting it. We have the positive, right? And then we have the negative. And then we have R, which is this. This is our vector, R, which tells us how far it's been displaced. And then we have Q, which is this being the amount of charge, right? This is not a vector. This is a vector. Is this how we denote the vector? I don't remember. I'm not a physicist. I'm I'm not a chemist. I'm not a physicist. I'm barely a mathematician. Right? Then it would make sense that mu, close enough, mu would be equal to this times q, because then it's basically kind of like momentum. Kind of. It's like an electric momentum. That's the best. No, wait, no, because momentum is this stuff. That's the best analogy I can come up with. It's not a good one. So just like when you walk, would walk be a better analogy? No. Maybe. Wait, maybe walk would be this analogy. Don't compare in physics. Well, am I supposed to just leave it at that? You make a mess. I'm already making a mess. It actually is a nice analogy. Yeah, okay. So I am getting it. I mean, it's not a good analogy, but you get what I mean. So like, it's the amount of displacement. So just like you can take an object and multiply the amount of displacement of that object by its mass, the same way you can take this, which is the displacement, and multiply it by charge, which would be the mass in this. This is not a great analogy, but you know what? We're sticking with it. Cool. Oh, makes sense. I'm lying to myself. It doesn't. It doesn't make sense. This is witchcraft. Then no. I'm trying to approach these are like classical mechanics, which is a bad idea. Hi, the A guy. Oh, this is okay. Cool. D is the debuy unit. I'm gonna debuy myself. I'm gonna debuy quantum mechanics after this live stream. Cool. You express dipole moments. It was named after Peter Debye, Dutch-American physicist who pioneered the study of dipole moments and electrical interaction between particles. He won Nobel Prize for Chemistry in 1936. He probably knew what he was doing. Nobel Prize, I know. Okay, how dipole moments are measured. When a solution of polar molecules is placed between two oppositely charged plates, they will tend to align themselves along the direction of the field. This process consumes energy, which is returned to the electrical circuit when the field is switched off. An effect known as electrical capacitance. I told you this would come in handy. Is this how capacitance works? Oh, it makes sense. Oh, it makes so much sense. Capacitance. It makes so much sense. Wow, this is phenomenal. This is amazing. We finally got past the point where I understand nothing, and we're getting into the point where I understand something, and it's phenomenal. It's the best feeling. You know what? If you're ever one of the drugs, I just recommend getting this feeling first, because listen, drugs are cool and all, but have you ever studied something complex and then all of a sudden it clicked? Oh, this is great. Oh, yeah. Measurement of capacitance of a gas solution is easy to carry out and serves as a mean of determining the magnitude of dipole moment substance. This capacitance, that's cool. Science is the best drug. It really is. Okay. Dipole moments as vector sums. Yes. Now I know. I'm so glad we paused to actually break this down, because it'd be so much easier now. In molecules containing more than one polar bond, the molecule's dipole moment is just the vector combination of what can be regarded as individual bond dipole moments. Being vectors, these can reinforce or cancel each other depending on the geometry of the molecule. It is therefore not uncommon for molecules containing polar bonds to be non-polar overall, as in the example of carbon dioxide. Yeah, so basically in order to get the total dipole moment, you just add together all of the individual dipole moments. Hold on, I got it. Oh yeah, an analogy like, you know, when you have voltage, coughing is part of scientific day-to-day. That is true. I would say it's an actually key element of science. Mathematics is by far the greatest drag. I don't know. Have you ever done chemistry? I mean, honestly, quantum chemistry, it's a strong contender. But learning science, something snapped out of me now after 788 years. I understand what it meant. And then I suddenly snapped. Okay. Oh, this is... Oh, great. The zero dipole moment of carbon dioxide is one of the simplest experimental methods of demonstrating the linear shape of the molecule. H2O, by contrast, and I don't... Oh, wait, H2O... H2O is something, I don't remember exactly what that molecule was. By contrast, has a very large dipole moment, which results from the two polar HO components oriented in an angle of 104.5 degrees. So it won't exactly be a sum, because they are still working against them. We could actually work out mathematically it by ourselves, but there is no point. The non-bonding pairs of oxygen are contributing Let's try it again. The non-bonding pairs of okay, third time the charm. The non-bonding pairs on oxygen are a contributing factor to the high polarity of water molecule. In molecules containing non-bonding electrons or multiple bonds, the electronegativity difference may not correctly predict the bond polarity. A good example of this is carbon monoxide, in which the partial negative charge resides on the carbon, as predicted by its negative formal charge below. Is it mathematics and science? I actually don't know. I think maybe. That actually stumped me. Wait, harder than it should have. I actually don't know mathematics and science. It doesn't rely on empirical methods. Yeah, I would even argue that it goes against empirical methods. I would even argue that it's like the opposite. If in physics, for example, if you create a model which doesn't align with the real world, you change the model. In mathematics, if you have a model which doesn't align with mathematics, you can change the mathematics. Do Google Docs support LaTeX syntax or something otherwise lame? Lame to use? Well, they do support. That's what's so nice. They do. In equations, you can do brag. Yeah, well, kind of. LaTeX. It's a bit of a simplified LaTeX, but you know, you can do stuff. Maths is the only exact science. The bit was natural sciences. Yeah, I think. You know what? I don't think. You know what? Let's just all agree to disagree on the fact that I just don't think, and I'm gonna leave y'all to figure out if maths is science. You know what? Yeah, actually. That's about as good a moment as any to start a poll, I think. Is maths a science? Overall speaking, it is a science. We're gonna do some science to find out. 4 votes, 50-50. Oh. Oh, it's really close. 14% of difference. There we go. Electron densities in the molecule and the dipole moment on unbalanced electron distribution it can produce are now easily calculated by molecular modeling programs. In this example, for methanol, see so carbon, 3 hydrogens, oxygen, hydrogen. The blue area centered on hydrogen represents the positive charge. So I'm assuming the red one will be a negative charge. I don't want to get started on the negative positive again. The red area centered where we expect the lone pairs to be located represents a negative charge. Okay, while the light green around methanol is approximate to neutral. The manner in which the individual bonds contribute to the dipole moment of a molecule is nicely illustrated by a series of chloromethanes. Okay, makes sense. So right here we have the strongest dipole moment because here all of them are the same, so they just cancel each other out. Here, and this is the strongest one, and then here they slowly balance out yet again. So you can narrow down true scientific theories by identifying the false ones. It's kind of what I'm doing on these live streams, actually. We're getting the true answer by identifying everything I say as false. Apparently, math is considered to be one of the foremost sciences. I think we're not here to argue what if it's considered to be. Actually, you know what? Yeah, we are here to argue if it's considered to be because, well, that's what the poll is about. We are checking if people consider math to be a science more than if it's actually a science. Actually, then, who am I? I would go against it. I have a poll right here proving quite the opposite. Based on my research with sample rate of 7, math is not actually considered a science. Ionic compounds, okay. Oh, ionic, the best behaved ones, basically. The shared electron pair model, introduced by Jane Lewis, showed how chemical bonds could form in the absence of electrostatic attraction between oppositely charged ions. As such, it has become the most popular and generally useful model of bonding in all substances other than metals. A chemical bond occurs when electrons are simultaneously attracted to two nuclei. We've already been over this. I feel like this is the 4th or 5th chapter where we're repeating the exact same thing. Different kinds of... yeah. Yes, the resulting substance sometimes said to contain an ionic bond. We've already been over this like 7 times. Is this such a... is this such a thing as an ionic bond? Well, I sure do hope so. We just spent 7 different sub-chapters talking about them, so I sure do hope so. When two elements form an ionic compound, is an electron really lost by one atom and transferred to the other one? Well, otherwise it wouldn't really be a bond if it was just transferred, would it? And they would just exchange electrons. Yes, ionic bonds exist. Blasphemy. Heresy. In order to deal with this question, consider data on the ionic solid lithium with fluorine, I'm assuming. The average radius of the neutral lithium atom is about 2.52 angstrom units, I think, if I remember correctly. Now, if this lithium atom reacts with an atom of fluorine to form lithium fluorine, what is the average distance between lithium nucleus and the electron it has lost, in quotes, to the fluorine atom? The answer is 1.56 angstrom units. The electron is now closer to the lithium nucleus than it was in neutral lithium. That's interesting. That's really interesting. Am I studying this for college or what? No, I'm studying, yeah, you know, yeah, Dark Vader is precisely. I'm studying it for a video on transistors. That's a long way ahead of us. Okay. That is a really interesting fact though, which means that in a bond, it makes sense if you think about it, but still, in a bond, it's not, the electron is not only getting closer to the other atom, it's also might get closer to the atom it came from. So the answer to the above question is both yes and no. Yes, electron that was now in the 2s orbital of lithium is now within the grasp of fluorine 2p orbital, but no, the electron is now even closer to lithium nucleus than before. So how can it be lost? The one thing that is really unarguable, damn it, this is, reading is hard, okay? Quantum mechanics is easier than reading. So how can it be lost? The one thing that is inarguably true about lithium fluorine is that there are more electrons closer to positive nuclei than there are in the separated lithium and fluorine atoms. Yeah, to both of them. But this is just the rule we stated at the beginning of the unit. Beginning of this unit. Chemical bonds form where the electrons can be simultaneously near two or more nuclei. Yeah, but we didn't say they can get closer to the second one too. Was the topic of the stream the same as previous 3 live streams? The exact same. From the same textbook as previous 10 live streams. We've been at this for quite a while. Progress is being made though, very slowly. The next chapter is gonna be better, I'm certain. Okay, I feel like we're circling over the exact same thing as numbers combination. Yeah, I know, they're models. Let's move on. We've been over this. Election pair repulsion. Yes. Oh, are we going in there? We already went in there. Damn it. Not again. No, not again. I'm just looking for some new information. And there was directions, aspiration. Yeah. Non-bonding electrons. Wait, what? This is interesting. If the central atom also contains one or more pairs of non-bonding electrons, these additional regions of negative charge will behave very much like those associated with the bonded atoms. The orbitals containing the various bonding and non-bonding pairs in the valence shell will extend out from the center from the central atom in directions that minimize their mutual repulsions. If the central atom possesses partially occupied d orbitals, it may be able to accommodate 5 or 6 electron pairs, forming what is sometimes called an expanded octet. That's interesting. Alright. Diagonal and trigonal coordination. As we stated above, a simple triatomic 3-atomic molecule of the type AX2 has its 2 bonding orbitals 180 degrees apart, producing a molecule that we describe as having linear geometry. Examples of triatomic molecules for which VSEPR theory predicts a linear shape are beryllium with chlorine, I think, which you will notice doesn't possess enough electrons to conform to the octet rule, and carbon dioxide. If you write out the electron dot formula for the carbon dioxide, you will see that the carbon-oxygen bonds are double bonds. This makes no difference to the VSEPR theory. The central carbon atom is still joined to 2 other atoms, and the electron clouds that connect the 2 oxygen atoms are 180 degrees apart. Okay. Are these study streams? Yes, they are. On this channel, yes. Actually been streaming on the channel for quite a while. 10. More like research. Yeah. Well, yeah, that's true. Or maybe... never healthy mix. Alright. Trigonal molecules. In an AX3 molecule, such as... what was it B? I don't know what's B. Fluorine-free, there are 3 regions of electron density extending out from the central atom. The repulsion between these will be at a minimum when the angle between any 2 is 360 divided by 3, 120 degrees. This requires that all 4 atoms be in the same plane. The resulting shape is called trigonal planar or simply trigonal. Okay. Beryllium? Is it really beryllium? Isn't beryllium Be? Okay, let's go for my favorite chemical website on the internet. ptable.com. Beryllium is Be. Boron, you say? Where's boron? Ah, there's too many of them. Chemists should really get rid of some of these. There's just too many to keep track of. No, control F. Boron, it is B. I'm blind. Okay. 5. Yeah. Okay, so it is boron. Dark Vader, are you a chemist? You seem to know an awful lot about chemistry. Kind of suspicious, you know? We can't get rid of them, that's why they are called elements. You know what? When I hear we can't, that just sounds like a lack of will, in my opinion. Have you ever tried, though? Is maths a science? 50-50. I'm proud. Alright, methane, CH4, contains a carbon atom bonded to 4 hydrogens. What bond angle would lead to the greatest possible separation between the electron clouds associated with these bonds? In analogy with the preceding 2 cases where the bond angles... Wait, oh, this one is in 3 dimensions, that's interesting. You might guess 360 divided by 490, but no, we have 3 different dimensions now. So if so, you would be wrong. Haha, I didn't assume that because I actually work in Blender, and over there I've already been screwed over many times by this assumption. The latter calculation would be correct if all atoms were constructed on the same plane. If not, we will see cases where this happens later. But here there is no such restriction. Consequently, the 4 equivalent bonds will point in the 4 geometrically equivalent directions, in 3 dimensions corresponding to 4 corners of a tetrahedron connected on the carbon atom. The angle between any 2 bonds will be 109.5 degrees. This is called tetrahedral coordination. Makes sense. Music stop. There we go. Make it when you use Blender. Do you use Blender or Blender? I have no idea what you're asking me. Kind of forgot. Oh, I love that nickname so much. Hold on, let me just fix up an animation in the meantime. If you want to know something some slurs from my language, cool. It's a cool thing to study. Alright. There. Consider the animation setup. Let's get back to research. So, this is the most important coordination geometry in chemistry. The geometry is also at the heart of semiconductors. Ooh, interesting. This and could be considered the most important geometry for electronics, at least at the molecular level. So we are actually finally getting into the meat and potatoes of this research. I don't know what to call the session. It is interesting to know that tetrahedral coordination of carbon is in most of the organic problem was worked out in the 19th century. We don't care about history. The direct method of 10 molecular shapes were developed. For example, it was noted one methane. Okay. We're done with the 6th subchapter. Oh. We've been stuck on this subchapter for how many live streams? Oh. There we go. Crystallography. Finally, something new. Although to be fair, we have seen some new things. Like for example, the dipole, right? This live stream, or the methane and carbon dioxide science for global warming with like the energies. There weren't energy states. Those were oscillation stuff where you shine a photon at the molecule. Magic. The point is, this is a subchapter. Yeah, that was a subchapter. That was just a subchapter. And now we're going into the first sub-chapter of a sub-chapter of a chapter. Introduction to crystals. Let's get into it, everyone. Oh. Okay, deep breath. Let's begin. Delicately. Hold on. Oof. Give me a second. You know what? I need a. Open the window. This is. Oh. Oh. I didn't breathe, honestly. Some Olympic level stream research I'm doing here. The delicately substance surfaces of large crystals that occur in nature have always been a source of fascination and delight. In some ways, they seem to represent a degree of perfection that is not apparent in other forms of matter. Okay, can we skip over the intro? Just time saving. Bro does not... Don't say bro. Come on, mate. And I praised your... You would come in. I compliment your nickname, and then you just... And that's what you do then? Come on. Oh, hi there, Joshua. Well, hi. The point is, symmetry elements. One of the most apparent elements of this geometrical regularity are the sets of parallel faces that many crystals display. Nowhere is this more apparent than in the cubes that develop when sodium chloride crystallizes from a solution. We usually think of cubic shape in terms of the equality of its edge lengths and 90 degrees angles between its sides, but there is a more fundamental way of classifying shapes that chemists find very useful. This is to look at what geometric transformations, such as rotations around the axis, we can perform that leave the appearance unchanged. This will be a wild ride. Alex, that's not it. Like, that's not reassuring at all, mate. You can't just join in and be like, "This will be a wild ride" with no context. I'm already struggling. I was here all along. Yeah, I know. That's why I said, you know, funny, because that was the bit. I was acting as if you just joined in. No, okay. Cubic symmetry. Actually, this is all pretty interesting, right? This is just symmetries. Okay, this is just basic math. Imaginary symmetry planes that mirror the portion of the cube. Yeah. Cube can, although anyone can recognize a cube when they see one, it turns out that many crystals, both natural and synthetic, are for one reason or another unable to develop all of their faces equally. Thus, a crystal that forms on the bottom of a container will be unable to grow any faces that project downward for a simple reason: there is no supply of ions or molecules from that direction. The same effect occurs when a mineral crystal tries to grow in contact with other solids. Finally, the presence of certain impurities that selectively absorb to one or more faces can block the addition of more material to them, thus either completely inhibiting their formation or forcing them to grow at slower rates. These alternative shapes can develop from a single basic crystal type, and these alternative shapes that can develop from a single basic crystal type are known as habits. Sorry, I meant to say this will be fun to watch. Come on, mate. Come on, mate. This is not helping. Not helping me at all. I'm losing confidence in myself. Sure, it's fine. It's fine. It's gonna be fine. Just make it. It's just chemistry. How bad could it possibly be? It's just chemistry. It's not difficult, is it? Yeah, it's easy. It's simple. It's simple. I'm fine. 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 Okay. Crystal habits. Sodium chloride grown from pure aqueous solution forms simple cubes, but the addition of various impurities can result in habits that can be regarded as cubes that have been truncated along planes normal to some of the symmetry axis. The same effects can sometimes be seen as a crystal slowly dissolves and material is released more rapidly from some directions than others. Okay. In this example, the perfect cube, 1, develops triangular faces at the corners, 2. If these enlarge beyond their maximum size, 3, the triangular faces meet a new set of edges that are hexagonal, 4. Eventually, they are left with 8 faces of what is obviously a regular octahedron. This, cool. Chilling, don't worry. Yeah, I'm precisely, I'm chilling, I'm fine. Make it your beginning sound legitimately. I'm not insane. I'm fine. I'm saying. I'm very much saying. I'm not insane. Come on, you come. I'm not insane. Come on, what do you think I'm insane? No, I'm not insane. Come on. You're calling me insane. Let's go on. One might think that these 5 shapes bear no relationship to one another, but in fact they all possess the same set of sets of symmetry. Same set of symmetry elements as the same set of symmetry elements as the simple cube, and thus various habits of the same underlying cubic structure and belong to the cubic crystal system described further below. Okay. What chemistry does to a man. What science does to a man, honestly. Alright. Even though a given crystal may be distorted or broken, the angles between corresponding faces remain the same. Thus, you can crush a crystal underfoot or break it up with a hammer, but you will always find that the fragments possess a limited set of interfacial angles. Makes sense. Okay. Cleavage planes. When a crystal is broken by applying force in certain directions, as opposed to being pulverized by a hammer, it will often be seen to break cleanly into 2 pieces along what's known as cleavage planes. The new faces thus formed always correspond to symmetry planes associated with a particular crystal type, and of course make constant angles with any other faces that may be present. Yeah, okay, so far it all makes sense. This is geometry. With chemistry. Of course. This is just history. I don't care about history. It's actually a personal goal of mine to not talk about history of anything on these streams, because we're kind of trying to power through. Are these supposed to be for molecules of a crystal or the blocks? What do you mean by blocks? What blocks? Hi, the pigs! Hi, welcome. The modern interpretations of these observations replaces I won't even attempt to pronounce that primal shapes with atoms or molecules, or more generally with points in space that these define the possible locations of atoms or molecules. It is easy to see how plane faces can develop along some directions and not others if one assumes that the new faces must follow a linear sequence of points. Okay. So square, parallelogram, rectangular, rhombic, centered, hexagonal. Yeah, why the fish? why fish and birds? Although everyone has seen and admired huge variety patterns on printed fabrics wallpapers, they are aware that these are based on 5 types on 2-dimensional unit cells. Okay, yeah, this is all kind of basic stuff, right? Then we have 3 dimensions. The unit cell of the graphite form of carbon is also a rhombus. In keeping with the hexagonal symmetry of this arrangement, notice that to generate this structure from the unit cell, we need to shift the cell in both the x minus and y minus directions in order to leave empty spaces at the correct spots. We could alternatively use hexagons as the unit cells, but the x plus y shifts would still be required, so the simpler rhombus is usually preferred. Okay. So flip. Am I? No idea. Mickey, how can you skim through this? How do you know what you're learning if you don't read every single word? Precisely. Well, that's my secret. Hey guy, I don't know what I'm learning. I have no idea what I'm doing. That's why Alex is in chat actually. So like, I pretend to know, and then Alex actually knows. That's kind of symbiotic relationship, you know. I pretend to know, and then I pretend to know but don't know, and then Alex just knows, and that's how we do it on these streams. It's easy. I don't have to read this. Make it after literally 2 minutes. Why is this? Hold on. Why? How? But okay, there is a reason though. Because you see, once I get confused, then it clicks. And when it clicks, that's content. That's why I do it. That's not symbiotic, that's dependent. Shit, we have to get into the linguistics of it. Symbiotic, parasitic, who cares? Am I right? It's fine. It's wet, it's fine. That's how it is. Yeah, come on, Alex, come on, mate. You're fine, right? Right? Yeah, it's good. Just hire Alex. Alex is my unpaid intern. It's the symbiotic relationship where Alex helps me and I give him nothing in return. You know how it is. The biologist within me just feels irritated. Then give him a raise. You know what? You're right. You know what? You are right. Alex, I'm doubling your pay. There. You all happy? You know what? I'm feeling charitable today. Alex, I'm tripling your pay. See? I'm a good person. See? It all worked out pretty well. 2 times 0 is still 0. Well, come on, this is not a mathematics live stream, Joshua. Oh, so what? Now I can buy 3 times as much of nothing. See? It all worked out perfectly fine. Speaking of changing the subject, we saw above that 5 basic cell shapes can reproduce any design motif in 2 dimensions. How about 3? If we go to 3-dimensional world, oh wow, I've actually asked the precise question. Of crystals, there are just 7 possible basic lattice types, known as crystal systems, that can produce an infinite lattice by successive translations. There are only 7... Well, yeah, I just read it, so I don't know why I should repeat myself. I'm unionizing. No. Listen. Unions are off. Have you all, by the way, speaking of, have you all seen the... Alex, you know what? Let me show you a video, which I just want to show you a video. All right, just one quick video, one quick watch before you unionize. Let me just show you one real quick vid. Just hope maybe it will change your mind.
We're excited to have you at this training, specifically designed to give you the tools that you need for success when it comes to labor organizing. During this course, we'll cover several important topics, such as our position on unions, associate rights, signs of employee disengagement, and how to identify, escalate, and address associate concerns. We are not anti-union, but we are not neutral either.
Yeah, neither am I. I'm not anti-union. I'm not anti-union. I like unions. They just, you know, they're not efficient, is all. That's my only problem, you know? I'm not anti-union. They're just not efficient. And I feel like, you know, it's much easier when it's like a direct thing, you know? Yeah.
We will boldly defend our direct relationship with associates as best for the associate, the business, and our shareholders.
Yeah, I'm not against unions. I just want to protect the workers from unions, you know? That's what I want to do. I want to... Don't stand on unions over this. I'm just using... It's a helpful graphic. That is all. It's a helpful graphic is all. I'm just saying, I just want to protect all of the make it workers from union heads, because they're just saying.
We do not believe unions are in the best interest of our customers, our shareholders, or most importantly, our associates.
See? They're not in the best intents of our customers and shareholders. Those are the only 2 important ones, actually.
Business model is built upon speed, innovation, and customer obsession.
And unions are inefficient. Is that a hanging... Oh, I thought that was the guy who was hanging. Never mind. And unions are inefficient, and that's why they're bad. That's why we should bust them.
Things that are generally not associated with unions. When we lose sight of those critical focus areas, we jeopardize everyone's job security. We don't badmouth.
Precisely. You see, union. That's dark. That's terrifying. Honestly, that's terrifying. This is cyberpunk. Oh, that was 5 years ago, by the way. I uploaded 5 years ago. We don't know exactly how old the video is. 2018. Me as a one factory when Walker is on the Alex. It doesn't matter that Alex is the only Walker. I still don't want Alex to unionize. But yeah, this video is
unions in general,
really
but we will
terrifying.
speak openly with associates about unions, including any specific concerns about particular.
It's also filled to the brim with BS. We're not anti-union, we're pro-shareholders, yeah. I mean, this video really is awful. It really is awful. Come to an highly combustible lemon.
Unions involved
And
in
only
organizing.
gets worse, by the way.
And we share our preference for a direct working relationship frequently and boldly, even when no organizing activity has occurred. You will learn about the warnings.
It gets so much worse because I'm pretty certain the next bit is for the managers. So I think, if I'm not mistaken, what you've seen so far was for the workers. This is the managers.
Most commonly associated with early union.
Recognizing the warning signs of organizing. Because why bother union busting where you can hire someone to union bust for you, right? That's much better.
In organizing, as well as other warning signs that could indicate associate disengagement.
And the reason, and like the examples are even worse. Like it gets worse than this. It's worse than this actually.
Vulnerability to organizing.
Don't worry,
we have
it gets
a right and
worse.
responsibility to share that a direct able to
Yeah.
do that effectively turns prompt and by their assigned ER managers or ER principals with unions or union-led movements like living wage or steward. Petitions or other concerted activity, such as an associate purporting to speak on behalf of his or her coworkers when raising concerns. Union graffiti, union t-shirts, hats, jackets, or other clothing, union flyers, and union visitors in or near the parking lot. Some signs
Living
are
wage
less
is a bad word. Yeah, these greedy workers. Well, all of a sudden you want to survive? Oh, what? So no, you just want to work only one day job, huh? These greedy workers. These poor shareholders, you know? They're investing their millions and are only getting tens of millions in return. You know why? That's because the workers hoard all of the wealth. That's why. Friends data to be here. Hi, they're hungry, by the way. Don't mind Woodward. You know what? Yeah, that's enough of that. So, in conclusion, Alex, remember if you imagine wanting to have a war contract. Precisely. Why would you want this pesky war contract and such? Just Uber exists, okay? So much easier. So to conclude, right, Alex. I get that you want to unionize, but just remember, just think of the poor shareholders, alright? You wouldn't want to take away money from the shareholders' pockets, right? Look at them, just barely scraping by on their merely millions of dollars, okay? I agree with unionizing. No. We've just talked about this, right? But don't unionize. Back to the coal plant. Precisely. Oh, hold on. What are we? Oh yeah, right. These are the 7 ones, right? Yeah. So cool. There are only 7 then. Wait, what's the difference between these two? It's not able to see. So I'm guessing there has to be a difference between them, because from a mathematical point of view, you could just define all of them in one definition. So there will have to be a difference between them. So basically when all three are equal, two are equal, or, well, one is equal, I guess. Here's all the shareholders. No, I'm not. There are Make It shareholders. I'm the streaming Make It. Well, to be exact, I'm the charity Checkups Make It. Then you have the shareholder Make It's. Or someone clearly has never seen the Make It video. Anyhow. And yeah, and then we have basically different these, yeah. Okay then. I'm not memorizing all this, there's no way. There's 7, that's too many. I can barely memorize all of the SI units, and there's only 6 of those. Lines and planes in unit cells. The Miller Index. Wait, why didn't we unionize and start a cult? Why unionize? Just start a cult. There's no need to unionize. Come on. Come on, alright? Come on. You're hungry. You're so silly. Don't union. Oh, Bob. No. We can just go with the cult part. There's no need. There are 7. No, Alex, there are only 6. There aren't 7 SI units. There are 6 SI units. In fact, there's meters, kilograms, seconds, kelvins, amperes, and candela. 6. No. There are 6. There are 6 SI units. Meters, seconds, kilograms, amperes, kelvins, and candela. Those are the only 6 SI units. There are 6 of them. So, yeah, I'm glad I can teach you all something cool about SI and how there are 6 units, in fact. Why isn't mol there? because mol is not a unit. That's why. Mol is not a unit. It's a constant. Anyhow, indexing lines in 2 dimensions. My favorite one. Well, I'm sorry to say, but mol is not a unit. So, yup. Sorry about that one. If you had to learn, but yeah, it's a constant. It's a constant. It's not a unit. Anyhow. To understand indexing, it will be easy to begin with... Oh, hold on. Have a convenient way of specifying the orientation of elements relative to unit cell. This is done by assigning to each such element a set of integer numbers known as its Miller index. Okay, so we have Miller index. Ooh, right here. To understand indexing, it will be easy to begin with a unit cell plane that we are viewing from above. Along each invisible z-axis, along the invisible z-axis, so like that. Okay, cool. So this is a plane, makes sense. The drawing shows a plane with 3 lines crossing it at various slopes. The index of each line is found by first determining the point where it intersects the x and y axis as fractions of the unit cell parameters a and b. That's the above example. Okay, makes sense. 2 is infinite b because it basically divides by 0. So hold on. Planes and Miller indices are so worthless. I trust you with my life. I trust you with my life. We're skipping over them. Precisely! Remember, unions are communist, okay? You dirty commies. You have to make an exception because the... It's not. Church of Union of Make It. The Church Union of Make It. Oh, that's a good name. That is a good name. I'm 99% sure you won't need them for anything practical. Alex, I already told you, I trust you with my life. We're skipping over these. You are getting bullied. Please no. Listen, if you got bullies, send them to me, and I'll blow them up. I mean, to tell them to quit bullying or something. Close packing of identical spheres. Square packing, hexagonal pack. Yeah, this is the dark mode is really gonna screw over these graphics. Crystal of course, three-dimensional objects. This is just orange packing problem, right? This will make it easier to develop some of the basic ideas without the added complication of getting you to visualize in 3D. Which is kind of funny because I'm really good at visualizing in 3D actually. I'm kind of used to it, so I'm just giving myself an out if they come back up. I think you can skip crystals. We don't need them for that. For what? I don't know. I have no idea. As if I'd know. I don't know. I'm not a chemist. I'm not a physicist. I'm barely a mathematician. Told you all already. This is the difference in marble and Peter Square. Okay, this is all basic. Yes, okay, so this is all basic. So coordination number would be just around, right? So a line would have a coordination number of 2. Right? I have no idea. Can be in numerical as possible. Okay, so if the atoms are identical and are bound together mainly by dispersion forces, which are completely non-directional, they will favor a structure in which as many atoms can be... Okay, makes sense. Yes. I'm really tired. Oh, mate. We're all tired on these live streams. Directed chemical bonds between atoms have a major effect on the packing. The version of hexagonal packing shown at the right occurs in the form of carbon, known as graphite, which forms two-dimensional sheets. Each carbon atom within the sheet is bonded to 3 other carbon atoms, resulting in a basic hexagonal structure with some atoms missing. Okay, makes sense. All makes sense. We answered not precisely. The underlying order of a crystalline solid can be represented by an array of regularly spaced points that indicate the location of the crystal's basic structural units. This array is called a crystal lattice. Crystal lattices can be thought of as being built up from repeating units containing just a few atoms. Okay. 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 Act. What is the rubber stamp? Present the paper, move, translated by amount equal to a space nothing, and stamp the paper again. Okay. Yeah, and then just repeat them. Because crystals. Sick. Sick. Neat. Sick. This really seems like basic math. This really does seem like just basic math. Yeah, this is just 3D. And I'm kind of good at that with the whole blender thing. I'm repeating in polymers, not in this way. No, polymers would be two-dimensional. I mean, damn it. Actually, not two-dimensional. Polymers would be... as a line, I don't know how to describe that. You get what I mean, right? There are a lot of different ways to arrange atoms. I mean, that's kind of a summary of this whole chapter. Seems like a summary, at least. You know what? If I get confused by anything, we can just go back. But this really seems simple. What is an ionic solid? Typical properties. What kind of elements contain? Define the lattice energy of an ionic solid in terms of energetic properties of its common elements. Hold on. Is it in this chapter? Why is the fourth subchapter an introduction? Why is the fourth subchapter an introduction? Not the first one. Okay, doesn't matter. The point is, lattice energy. Something we'll learn in this chapter, right? Okay, cool. Let's mention. Sick. Ionic solids. The idealized ionic solid consists of two interpenetrating lattices of oppositely charged point charges that are held in place by a balance of Coulombic forces. Example, NaCl, I guess. I think. Will you start a live stream in your gaming channel where you create a Minecraft SMP and the viewers can join too? Maybe. We had a plan for that, but it kind of dissolved. Chemistry pun. But because real ions occupy space, no such perfect ionic solid exists in nature. Nevertheless, the model serves as a useful starting point for understanding the structure and properties of a small group of compounds between elements having large differences in electronegativity. Okay. Sodium chloride. Wow, it's what I just said, right? NaCl. The most well-known ionic solid is sodium chloride, also known by its geological name as rock salt or halite. We can look at this compound in both structural and energetic terms. Structurally, each ion in sodium chloride is surrounded and held by tension by 6 neighboring ions of opposite charge. The resulting crystal lattice is of a type known as simple cubic, meaning that lattice points are equally spaced in all 3 dimensionals and all cell angles are 90 degrees. So it's cube, basically. The cubes. Alright. In figure, this one you have drawn two hydra. Yeah, I mean, it's basic geometry, come on. Let's get the interesting bits. How geometry and periodic properties interact. Okay. The most energetic is time the charm. The most energetically stable arrangement of solids made up of identical molecular units, as in noble gas elements and pure metals, are generally those in which there is a minimum of empty space. These are known as closed pack structures. Considering there's minimum of empty space, that makes sense. And there are several kinds. In the case of ionic solids, of even the simplest one-to-one stoichiometry, not pronouncing that again, the positive and negative ions usually differ so much in size that packing is often much less efficient. This may cause the solid to assume lattice geometries that differ from the one illustrated above for sodium chloride. Makes sense. By way of illustration, consider the structure of calcium chloride. Spelling cesium is also used, CsCl. Cs is much larger, right? The radius of Cs plus ion is 168 picometers compared to 98 picometers for sodium. Makes sense. Makes sense. It's so much, much larger considering it's further down the periodic table. It's, to be exact, right here. It cannot possibly fit into the octahedral hole for a simple cubic lattice of chloride ions. The CsCl lattice therefore assumes a different arrangement. What is a different arrangement? Figures 1733, this one, I think, focuses on 2 of these cubic lattice elements whose tops and bottoms are shaded for clarity. It should be easy to see that each cesium ion now has 8 nearest neighbor chloride ions. Should be easy to see is relative, so as the back, as the front, as the back, as the front. So I mean, if you square, oh, I see it now. Okay, hold on. I can actually visualize this in Blender a bit better. Ah, there's mosquitoes in my room. Oh! Got them. This mesh to points, not mesh to curve, mesh to points, mesh to points, and then instance on points, and then icosphere. Like this, like this, like this, with subdivisions this, and then add icosphere with subdivisions high up. There we go. That's the one. Are you pro blender? Yes, I am. Amateur in it. What do you mean amateur? I'm a professional. I'm professional. Make tutorial blender. I did a couple years back. There we go. I think that's what it is, right? What does it look like? It looks like, right? This one is surrounded by all eight. That's an 8, not a 4. What's this again? This is this. Simple. Makes sense. Okay. Don't save. Now. Yeah, each core is surrounded by 8 cesium ions, precisely. So the last points are still geometrically equivalent. We therefore describe this structure as having 8-8 coordination. The two kinds of arrangement exemplified by NaCl, rock salt, and CSCl are found in a large number of other 1-to-1 ionic solids. And describe the structures of these other compounds. Yeah, okay. Alkali halides. Yes, this is cesium with chlorine. This was, because I already turned off. The interaction of the many atomic properties that influence ionic binding are nicely illustrated by looking at a series of alkali halides, especially those involving extreme differences in atomic radii. The latter are drawn to the same scale. On the energetic plots right, the lattice energies are shown in green. We will start with the one you already know well, sodium chloride. Okay, so this is the... Mm. 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 Don't get it. Kilojoules per mole always makes... Okay, we all know why mole is there. Just special. Okay, so... Extreme differences in atomic radii, okay. The energetic plots at the right, the lattice energies are shown in green. The arrow is going down. Is it because that's the energy required to create the solid, and thus this is basically the remember the bonding energies we did a while back? A while back? That seems like the same thing. Okay. I think that's the same thing. I have no idea. Tiny makes strong. A normal sentence. This is the most ionic of the alkali halides with the largest lattice energy and the highest melting and boiling points. We should... You know what, let's go back the chapter, because I think we missed the lattice energy. Nope, there is no lattice energy on this side. There's no lattice energy in this chapter. Okay. Can you tell a dark humor joke at the last minute of the stream? Why? And how dark, also? Website opens for good the homepage. That's funny. Dark humor is relative. How dark do you want me to go? And why? That's a more important question. Small size of these ions and consequently high charge densities together with the large electronic difference of the two elements places a lot of electronic charge between the atoms. Makes sense. What's your limit? Depends. There's one I really like. It's my Probably my favorite joke that I made, honestly. It's really short. It's basically a single sentence. And in my opinion, it's pretty funny. It's... okay, and it requires a bit of backstory. A bit. To fully appreciate. But okay, the point is, we have this. So the larger the distance, the smaller the energy. The 190, 187. Electrons in the nucleus. The cesium ion with its low charge density resembles a big puffball, which can be distorted by a hydrochloriding fluid ion. The resulting ion-induced dipoles, blue arrows, account for much of the land's energy here. Okay. The tiny lithium ion can't be very close. Yeah, it'll make sense. I'm getting concerned about studying chemistry. What do you mean getting... What's... in what way? Like getting concerned about... starting? Or... what exactly? What's your concern? What's on your mind? Alright, some properties of ionic solids. Oh, boy. This is a dense research session, honestly. Oh boy, oh boy, oh boy. We're getting close to MOSFETs. We're really close. Only 6 more sub-chapters. Oh, music stuff. There. Study biology. If I don't come on. Biology, really? Hold on, I'm fixing an animation. Thinking about getting deeper into chemistry. What's stopping you? To be fair, this isn't really chemistry but more solid state physics. Yeah, I should make this clear, right? I'm not researching. This is a bit more of a... That's how to actually describe what this actually is. Well, this is material science. So it's a bit quantum mechanics, a bit of chemistry, a bit of physics, a bit of... everything, honestly. A little bit of everything all of the time. I'm finished playing and I'm staying inside. That's full of smoke. So copy up the joke. But solids. Wait, hold on. Let me just check actually. How long till MOSFETs? A bit of math. Actually, not as much math. I don't know if you all know this, but we're not really doing all that much math, except for geometry in this case. But before geometry, we haven't really done all that much math. Why is back matter in the middle? And why is there a sub chapter in this? Why is there a sub chapter to a sub chapter to a sub chapter to a chapter? This is a sub chapter. Why? I am... It's fine, it's fine. Okay, so... once we're done with this, we'll have 1.8 sub-chapter. Your dog head, you like chapters. Oh, mate. Listen, I love chapters so much that I actually put a chapter in my chapter in my chapter. In my chapter. Oh, wow. That's a lot. That's a lot. Makes it actually quite hard. Makes it actually really difficult to quantify just how far away from MOSFETs we truly are. No, iron derived solids. Should we switch to the third chapter actually? Because I'm curious. This is getting a bit stale. Should we, as a try, should we do it? Let's do poll. This time I wanna turn this into a bit of a longer live stream. So. There, that's either way. A 100% yes. Starting at 3-3 should be enough. 3-3? You're crazy. That's... Conductors. Well, you know what? Actually, I would rather start at bonding in metals, honestly. There are no sub-chapters there, so, you know, this is only 2 chapters. It's not that far. Let's see, how long are they? Yeah, I mean... Should we really skip those? I mean, they don't seem that all that difficult. You have this one. And you have this one. Which is, well, kind of short. Oh, but I don't know what bands are. I don't know how bands work though. I don't know what bands are. I came across them before. I still have no idea what they are actually. I think you should take a break. No! Breaks are for cowards and weaklings. And we're neither. 100% yes. Okay, let's dip in them. Properties of metals. The fact that metallic elements are found on the left side of the periodic table offers an important clue to the nature of how they bond together to form solids. Being a lot of them. These elements all possess low electronegativities and readily form positive ions. Because they show no tendency to form negative ions, the kind of bonding percent ionic solids can immediately be ruled out. The metallic elements have empty or nearly empty outer p orbitals, so there are never enough outer shell electrons to place an octet around an atom. Bands are many possible energy levels close together, so we just say that there are so many small energy region that they are one big level. What, gentle reminder, what are energy levels? There were those. I'd like it. I'm not saying I don't remember. I do. I just, you know, in case someone doesn't get it on stream, you know, that's just what. Oh, that's the one. Never mind. Okay, I get. I mean, I knew it. I knew what they were. I remember. I remember what they were. I remember those. Yeah. I remember what those were. Yep. Nah. I'm learning Blender. Any tips? Just do stuff. That's it. Can you make what? What is that? I don't know what Pentfin is. Nice, yeah. I remember those. You like energize stuff, and then they are energized. The best. That's the best explanation of energy levels possible. Okay, hold on. Maybe I am a bit tired. The point is, properties of metals. Yes. These points lead us to the simplest picture of metals, which regards them as a lattice of positive ions immersed in a sea of electrons, which can freely migrate throughout the solids. In effect, the electropositive nature of the metallic atoms allow their valence electrons to exist as a mobile fluid, which can be displaced by an applied electric field, hence giving rise to their high electrical conductivities, because each ion is surrounded by the electron fluid in all directions. The bonding has no directional properties. This accounts for the high malleability and ductility of metals. Okay, so far, all makes sense. Alright. This view is an oversimplification, because of course this, that fails to explain metals in a quantitative way, nor can we account for the differences in the properties of individual metals. A more detailed treatment known as the bond theory of metals applies the idea of resonance hybrid to metallic lattices. In the case of alkali metals, for example, there's literally a lot of stuff. I must cover the electricity. Molecular orbitals in metals. Okay. Oh, what is this graphic? So we have lithium. I'm smart. We have lithium. Okay. Okay. So like we have. Okay. So. So that's such a physics picture. That's what? Hold on. Hold on. Whoa. Pound the brakes. What's happening? You have lithium 2 in 3 lithiums. I'm confused. This is no. I don't like this. Okay, origin of metallic properties. Let's just skip over that graphic. Molecular orbitals in metals. No. How about that, huh? No, just no. I'm saying no. I'm reserving my right to. No. And metallic solids possess special properties that set them apart from all kinds of solids and make them easy to identify and all of these properties derive from the liberation of valence electrons from the control of their atoms, allowing them to behave as what previously valence shell orbitals of the neutron atoms split into huge numbers of closely spaced levels known as bands that extend throughout the crystal. Melting point and strength, we don't really care about metals, we care about electricity. Electrical conductivity, there we go. Why are metals good conductors? Finally, we're getting into debate. Let me just get water. There we go. Alright. In order for a substance to conduct electricity, it must contain charged particles, charge carriers, that are sufficiently mobile to move in response to an applied electric field. In the case of ionic solutions and melts, the ions themselves serve this function. Ionic solids contain the same charge carriers, but because they are fixed in place, these solids are insulators. Okay. In metals, the charge carriers are the electrons because they move freely through the lattice. Okay, so like in metals, you have a lot of metal, and it's surrounded by a soup of electrons, and this soup moves electricity around. Right. Okay. In metals, the charge carriers are the electrons because they move. Yeah, they're very low mass inertia. Electrons allow them to conduct high frequency alternating current, something that electrolytic solutions are capable of. In terms of demand structure, application of an external field simply raises some of the electrons to previously unoccupied levels, which possess greater momentum. Yeah, that's a BS explanation, but in metal, the charge carriers can move more freely. What do you mean a BS explanation? It's perfect. You have metals and electron soup. No? Electron soup explains everything. I'm struggling. I'm struggling, man. All right. Okay, I think I get it though. I don't. I'm lying to myself again. I'm in denial. Wait, I get it because there is nothing to note. Well, there are no. I am. I think I'm mentally ill. It's fine. Fine. I'm fine. In metals, the charge carriers are the electrons because they move freely throughout the lattice. Yes. So, okay, fine. Yes. Hi, the stick. Hi, welcome. Okay. Neat. Empty MOs. What are MOs? What are MOs? The conductivity of the electrolyte solution decreases as temperature falls due to decrease in viscosity, which viscosity is in cause of coarseness, which inhibits ionic mobility. The mobility of the electron fluid in metals is practically unaffected by temperature, but metals do suffer from a slight conductivity decrease opposed to ionic solutions as the temperature rises. This happens because the more vigorous... I don't... MO molecular orbitals. Oh, I see. So we have... okay. Oh, this clears up. That clears the picture up. Okay. So we have empty molecular orbitals and completely filled molecular orbitals from atomic to s orbitals, and then they just move. That makes sense. Yeah, okay. Most metals are made of atoms that have an outer configuration of 2s, which we would expect to completely fill the band of molecular orbitals we have described. With the band completely filled and no empty levels above, we would not expect elements such as beryllium to be metallic. What happens is that the empty p orbitals also split into a band. Although the energy of the two p orbitals of an isolated beryllium atom is about 160 kilojoules, greater than 2s orbital to bottom line. Okay. Are you a time traveler? Because you know in which maker will get stuck. No, Alex just knows stuff. Cool. So bands are... Wait, so bands are just like energy... Wait, hold on. I went through the shit. You mean getting a girlfriend or this? Because it's one or the other. There's no way you went through both. I refuse to believe. Chemistry.band. That's not what I'm looking for. Chemistry band. Not what I'm looking for. No, not what I'm looking for. Physics, atoms, atomic bands. I don't know. Bands, bonds, bands, right? Bands. Band. Yes. Band gaps. Band structure. This one. There we go. You know what? Let me just... Sick. A band structure is a band structure also describes the range of energy levels that electrons may have within it, as well as... Why not just energy levels? Oh, because it's a range. As well as the state, as the range of energy that they may not have band gaps. Okay, so electrons can have the energy levels that are in a band, and if there's a band gap, that means the electrons can't have those. That makes sense. Well, I'm hoping it makes sense. We'll see. Okay, so we have overlapping bands, but right here we have a band gap. So far, it's okay. Okay. This diagram illustrates the band structure in ferro metals such as sodium or magnesium, and how it arises from orbital splitting in very small units, M2 and M6. The conduction bands for the infinite molecular Mn are shaded. Okay, so... Okay, Okay. Okay. This live stream is great ASMR, I gotta say. Just make it saying okay for 3 hours. Electrons live in the bands. Energy that would lie in the band gap. Wait, they live in the bands? Wait, they live in the bands? I thought bands were just the range of energy levels they can have. It's confusing. It's difficult stuff. I wanna go back to map. In map, everything is simple. Okay, so wait. So band is the... Wait, what is a band then? I'm confused. I thought that's what I meant. Oh. Okay, so band is just a range of energy levels they can have. So bands don't really exist in terms of electrons. Bands exist in terms of energies, right? So like you can't have an electron on a band, but you can have the energy of an electron on a band, energy level of an electron on a band, right? Alex, I should start paying you though. You know what? That's... I really should. I'm struggling. Only the outermost atomic orbitals form bands. The inner orbitals remain localized on the individual atoms, non-bonding. Oh, so bands happen in solid, not at the individual. Okay. Oh, I see. The electron can only have certain values of energy. The allowed energy values on the band, the forbidden ones are the band gap. Okay, yes. Okay, sick. Okay, then I do it. Okay, neat. Neat. Alright, cool. Quick, advance, so I get... Okay, there we go. Field levels cross band gap and extend into the upper band. Yeah, because there's a band gap, they can't go there, so extend above if... Okay. Upper band overlaps, lower band allowing a continuous range of levels to fill. Okay. Insulators and semiconductors. There we go. So, oh yeah, wait, before we go on, let me guess. Insulators will have a huge band, because then that limits the amount of energy levels electrons could possibly have, and thus insulates, because only incredibly high energy levels are allowed, because the band is large, so you know you need a really high energy level. And conductors won't have any gaps, and this would lead to electrons having more, let's say, freedom, and thus more possible energy levels are allowed, and thus you can conduct, right? Am I... Insulator, semiconductor has it... Hold on. Semiconductor. Okay. Yes! Insulator is characterized by a large band gap between the highest filled band and an even higher empty band. Oh, this... clicked. Okay, this band gap is sufficiently great to prevent any significant population, which also means that... Wait, if there is a band gap in every insulator, and if there is a conduction band in every insulator, this means that you can technically use an insulator as a conductor if you try really hard. If you try really hard. Okay, the presence of okay, characterized by a large band gap between the highest filled band and even higher empty band. Yeah, so by definition, insulators have an empty band, which means you can use... I'm just saying, you can use insulators as conductors if you try hard enough. That's all I'm saying. The presence of a very intense electric field may be able to supply the required energy. That's precisely what I said. In which case, the insulator undergoes a dielectric breakdown. Dielectric breakdown. Most molecular crystals are insulators, as are covalent crystals such as diamond. Okay. If the band gap is very small to allow electrons in the filled band below it jump to upper band, thermal excitation, the solid is known as semiconductor. Wait, is that how thermal, what's them called? Ah, the resistors that increase and decrease the resistance by with temperature. Is that how they work? They just have a band gap which changes in size depending on the thermal energy. Also, there are infinitely many bands on top of each other, but we only ever deal with the last full and first empty one. That's not helping. Okay, hold on. Many bands on top of each other, or do we only deal with the last full and first? That makes sense. Yes, because we don't really care about the already filled in ones. The ones that are filled in by default. We only care about the potential. Think. Okay, the point is, from bottom up, yes. Okay, in contrast, the metals will decrease the temperature. The conductivity of semiconductors increases with temperature. Alright, we don't really care about temperature though. N and P type materials, finally. Oh, NNT, we're finally getting into it. Okay, for example, a phosphorus atom introduced as an impurity into silicon lattice possesses one more valence electrons than silicon. This electron is delocalized within the impurity band and serves as the charge carrier in what is known as an N-type semiconductor. In a semiconductor of the P-type, the dopant might be arsenic, and let me guess, it misses. It's lacking in it, which has only 3 valence electrons. This creates what's amount to electron deficiency or hole in the electron fabric of the crystal. Although the solid remains electrically neutral overall, as this vacancy is filled with electrons from silicon atoms, the vacancy hops to another location, so the charge carrier is effectively a positively charged hole. Hence, P-type designation. Once again, this is going really confusing really fast because P stands for positive and for negative, and negative means more electrons, positive means hole missing an electron. So negative means more, positive means less. P-N junction, okay. When P and N-type materials are brought into contact, creating a P-N junction, holes in the P material and electrons in the N material drift towards and neutralize each other. Makes sense, creating a depletion region that is devoid of charge carriers. But destruction of these carriers leaves immobile positive ions in the N material and negative ions in the P material, giving rise to an interfacial potential difference, as depicted here. Okay, so as this charge builds up, it acts to resist the further diffusion of electrons and holes, leaving a carrier-free depletion region which acts as a barrier at the junction. Yes, okay, so we have right here, we use holes as carriers, right here we use electrons as carriers, and right here the holes and electrons cancel out, we have no carriers, no carry. Alright. When you do N phase reveal, it's A phase reveal. You use an N when stars are low. It's not, it's a phase reveal, not N. Simple conduction. I think we already went over conduction. Oh no, we actually haven't. Went over metals. Alrighty then. Our initial studies will more or less be a review of topics in electricity that you may have seen before in physics. However, if experience and guide, there is no great harm looking back over this material. There is great harm to my mental health. It seems that for many students, the whole concept of how electricity actually works is a little hazy. Considering that you hope to be called an electrical engineer one of these days, that's optimistic. Not really. Not really my kind of thing. This might be a good thing to know. When is the phase reveal? 100k? What makes you think that I will do a phase reveal? Can you imagine how boring that would be? Like, it doesn't really matter what my face looks like, even. People would be disappointed. That's my main issue with doing a face reveal. No matter what it looks like, people would just be disappointed. There's nothing interesting about my face. Most of the laws of how electricity behaves are really just mathematical representation of a number of empirical observations. Based on how I guess really okay. So including however, let's define a few quantities now. Total charge in some regions defined by symbol Q, coulombs, yes, of charge of an photon by little q or by e. For the things, and this goes starts to q. That's the q we've seen before. It's charge. Since charge can be distinguished throughout the region with varying conceptions, we'll also talk about charge density. Of coulombs per. Yes, so charge density makes sense. And then we have big Q as an integral of it because, well, that's what it's a function. Yeah, this is just the most basic usage of an integral you can possibly have. Alright, neat. The motion of charge gives rise to an electric current, which we call I. The current is measured, yeah, so amperes as coulombs per second. That's why we can have, okay. So when it comes to electrical, alright, so when it comes to carriers, we have either holes or electrons, but it doesn't matter what kind of carrier we have because both of them just move charge around. So no matter what kind of carrier we have, it should still be just amperes, right? Non-recoverable history, okay. In order to have some conduction, we have to apply a potential or voltage across the sample. We do this with a battery, which creates a potential difference, V, between one end of the sample and the other. We will make the simplest assumption that we can, and say that the voltage, V, gives rise to a uniform electric field within the sample. The magnitude of the electric field is given simply by E is equal to V divided by L, where L is the length of the sample, and V is the voltage which is placed across it. Okay. Should be showing E as well as forces, etc. as vectors in an equation, but since their direction will be obvious and ambiguous, let's keep things simple and just write them as scalars. Okay. Electric potential or voltage is just a measure of the change in potential energy per unit charge going from one place to another. Since energy or work is simply force times distance, if we divide the energy per unit charge by the distance over which that potential exists, we will end up with force per unit charge, or electric field, E. Okay, step by step makes sense. If you are not sure what you just read, write as equations and see that it is so. I think I get it. And actually, no, I do get it. Okay. The electric field will exert the force for charges. The force is given simply as the product of the electric field, strength times the charge. Makes sense. Or in other words, F is equal to Q times V divided by L. The force acts on the charge as the constant accelerated on the Newton's units of motion. Force is equal to mass times acceleration, which is just equal to... Okay. Yeah, so Q is the version... Okay, so Q is like... Mass makes sense, charge, right? We've already used that analogy before in the stream. Mass being like charge, or charge being like mass. Hide the Bilvis, and then... So E would be the analogous to... Well, that's actually pretty dangerous to... That sort of analogy. But the field would be analogous to acceleration. It makes sense. Thus, the velocity of a particle with no initial velocity will increase linearly with time as this. Oh, so far, it all surprisingly makes sense. For now. For now, it's all pretty simple. Yes, that's the slope. Cool. Although the particle achieves various velocities depending upon how much time there is between collisions, there will be some average velocity, which will depend upon the details of the collision process. Let's define a scattering time, which is tau s, which will give us the average velocity when we multiply it by acceleration of particle, that is this. Yes, so we have the average velocity, which is equal to... Wait, what was m? Hold on. Oh, we divide by m to get this. So m is mass. Okay, so the velocity will be equal to the average velocity will be equal to charge times the electric field times scattering time divided by mass. And then we can also get the scattering time of it. Okay, so why? Phenomenal question. Charge times electric field, that's simple enough, right? The larger the charge or the larger the electric field, these just work together. So we use it kind of as a... Yeah, it's fine, Mike. You can do it. It's fine. It's fine. We'll leave we'll leave transistors for the next live stream. New making more is great. Love the flying coffee. It's good to be back. Hi, the Pizza Ranger. Welcome back. Oh, we'll leave transistors for the next live stream, but I just want to finish this at least. Now let's take a look at just a small section of the conductor. So this will have a the cross section of the sample A, but will only be average velocity changing time along. So velocity times time, that's length. Where delta t is just some arbitrary time interval. So this is basically the amount of distance they cover in a arbitrary time interval with that average velocity. After time delta t has passed, all of the charges within the box will have left it, as they are moving with the same average velocity v, or v bar. If the density of charge carriers in the conductor is n per unit volume, the number of carriers capital N within our little box is just n times the volume of the box. Makes sense, right? That's how densities work. Thus, the total charge Q, which leaves the box in time delta t, is just Qn. The current flow, I, is the amount of charge which flows out of the box per unit time. Yes, so that's a step-by-step way to define amperes then. We now have two choices. We can look at our result from a field quantify point of view, in which case we will be interested in the current density, J, which is just current I divided by cross-sectional area, where sigma is called the conductivity of material. If we look at the conductor from a spectral point of view, then we are interested in the relationship between the voltage and the current. The voltage is the electric field times the length of the sample, and the current is just the current density times the cross-sectional area. Thus we have Ohm's law. This is cool. That's really cool. That's so cool. Oh my goodness. Oh wow, that's cool. Oh wow, that's cool. That's so cool. That's so cool. This is the definition of Ohm's law. That's amazing. Resistance is equal to... Yeah, I already used that in the video. That's amazing. The mobility is just the proportionality factor between the average velocity of a particle and the electric field. That is... okay. Oh, that's sick. It is indeed cool. That is beyond cool. Okay. I'm really like going into these aspects of research. But when it comes to the video, which I will be making about electricity soon, I can't wait to like visualize every single one of these, because all of these will be... it's not exactly... all of these will be relatively simple to visualize. And the interaction, that's really cool. Because most of the time, you know, when people get into electricity, They only learn about current voltage and resistance. But the way that's so sick. Oh my goodness. I'm tired as hell and it's still amazing. Going to be lit. It's going to be... I can't find a pun for electricity. I don't know, something with electricity. Ah. I feel like that's enough for the 2.5 hours. That's how long we've been streaming. 2.5 hours. Wow. Anyhow, that's the longest live stream we did in a while, actually. And for research live stream, that's a lot of time. That's a lot of time for a research live stream. Let me just set up one more thing. It's gonna be a shocker. There we go. I'm so tired. I can't even come up with a good pun. Thank goodness we have Alex. You know what? We should all just take a second to realize how fortunate we are to have Alex here with us. That's the joke. Oh yeah, right. Wait, but hold on. You didn't answer my question though. Why was I supposed to end the stream with a dark humor thing, joke stuff? Alright, there we go. Animation set up. I don't know, I just for fun. It's a pretty dark one. It's a decently dark one, you know. I don't know if I wanna. I do have one, but it's dark. It's quite dark, and I don't wanna end the live stream this way. I don't know if I wanna end the live stream with something this dark. Just tell it. Oh boy, it's I mean, I'm really proud of it. It's my own joke. I'm really proud of it coming up with that. But okay, fine. So let's pause the music. But then I'm just ending the stream there. So a while back, that's some bit of backstory so we can all appreciate, right? Just a bit of backstory so we can all appreciate the bit. A while back, I used to joke around when it comes to dark humor. I had a lot of different dark jokes, and dark humor was my favorite kind. So I was joking around a lot like that, you know. And I like pushing things. You know, I'm a big fan of the idea that you don't know where the line is until you cross it. And so I used to joke around a lot, and I have this friend who didn't like it one bit. He thought I was taking it too far. It's just dark stuff, and so you know, I just one day I just told him, you know, a single sentence bit. I told him, you know, oh, don't worry, soon I'll stop joking about suicide.